Ever wondered why time seems to slow down when you're near something really heavy or moving super fast? That's the magic of time, a concept far from ordinary. It's not uniform, it bends, it stretches, it's influenced by gravity and speed. This peculiar behavior of time is deeply intertwined with the marvels of the theory of relativity. Time dilation, an idea that time doesn't flow at the same rate everywhere, is a fascinating part of this theory. The theory of relativity is the key to unlocking these mysteries. So, what exactly is this theory of relativity? Let's start with the basics. The theory of relativity is actually made up of two parts: general relativity and special relativity. Both of these theories come from the brilliant mind of Albert Einstein, who shook the world of physics in the early 20th century. Special relativity, which came first in 1905, is all about the consistency of the laws of physics. It says that these laws are the same for all observers, no matter how fast they're moving or where they are. It's a bit like how the rules of a game of chess don't change, whether you're playing it on a train or a stationary table. General relativity, published 10 years later, added gravity to the equation. It describes gravity not as a force like we're used to thinking, but as a curve in space-time around a massive object. Imagine a heavy ball on a rubber sheet. It creates a dip, right? That's kind of how mass distorts space-time. Speaking of space-time, this concept is key to relativity. It's the idea that space and time aren't separate entities, but are woven together into a single continuum, so changes in one affect the other. In essence, the theory of relativity gives a whole new perspective on time and space. And as we'll see in the next scenes, it has some pretty mind-bending implications. Now let's delve deeper into the concept of time dilation and how gravity plays a role in it. Imagine you're in a spaceship, zipping around a massive star. Back on Earth, your best friend is chilling, sipping their favorite drink. Now, according to Einstein's theory of relativity, time for you in the spaceship would actually be moving slower than for your friend on Earth. This is what we call time dilation. But why does this happen? Let's think of time as a river. When the river is calm and flat, it flows at a steady pace. But when there's a big rock, or in our case, a massive star, it creates a dip and the water around it flows slower. This is how gravity influences time. The stronger the gravitational force, the slower time appears to pass. That's why time for you near the massive star is ticking slower than for your friend back on Earth. This isn't just a cool thought experiment. GPS satellites, for instance, have to account for this effect. They're further from the Earth's center and experience less gravity, so their clocks tick a tiny bit faster than ours. If we didn't correct for this, your GPS could be off by several kilometers. But it's not just massive objects that can cause time dilation. High speeds can too. If you could zoom around in your spaceship at close to light speed, time would also slow down for you compared to your friend on Earth. We'll get to more of that in the next scene. Just remember, gravity is like a big cosmic dimmer switch that can slow down time. The closer you are to a massive object, the slower time runs for you. So next time you're late for a meeting, just say you were hanging out near a black hole. So if you lived on a planet with super high gravity, you'd age slower than your twin on Earth. How fascinating is that? What about speed? How does that affect time? Now, that's where things get truly fascinating. You see, the faster you move, the slower time passes for you, relative to someone standing still. This is a concept known as time dilation. Let's imagine you're on a spaceship zooming close to the speed of light. For you, inside the ship, time would seem to pass normally. You'd eat your meals, sleep, and wake up just as you would on Earth. But for someone observing from Earth, your clock would appear to tick slower, and you'd seem to age slower. Why does this happen? Well, it all comes down to the speed of light being constant for all observers, regardless of their motion. This is a postulate of Einstein's special theory of relativity. Since light speed is fixed, if you're moving rapidly, time must slow down for you to compensate. Now let's take this idea a step further. What if you could reach near light speed? Well, time would slow down so much that you'd age significantly less compared to everyone else. A year could pass for you, but decades, even centuries, could have passed back on Earth. So, if you could somehow travel at near light speed, you'd experience time slower than everyone else. You'd age less. Just imagine the possibilities. You could become a time traveler of sorts, leaping forward into the future while barely aging. It's a mind-bending concept, isn't it? Now you might be wondering, does this all matter in the real world? Well, let me assure you it absolutely does. The theory of relativity, while sounding like something out of a science fiction novel, has some very tangible applications that impact our daily lives. Take GPS satellites, for example. These orbiting devices help us navigate our way around town or plan a cross-country road trip. But did you know that the clocks on these satellites are set to account for time dilation? Yes, that's right. The effects of both gravity and high-speed travel cause the clocks on GPS satellites to tick faster than those on Earth. To ensure accurate positioning data, these satellites are programmed to correct for this time dilation. And it's not just navigation systems that rely on the principles of relativity. Many other areas of physics and astronomy are also deeply intertwined with this theory. For instance, scientists studying black holes, gravitational waves, and even the Big Bang itself use the principles of relativity to understand these phenomena. Moreover, advancements in technology such as particle accelerators, nuclear power, and even your humble television set all owe a debt to the insights provided by the theory of relativity. So, the theory of relativity isn't just about mind-bending concepts, it has practical applications that affect our daily lives. Whether we're navigating unfamiliar roads, watching our favorite show, or marveling at the mysteries of the universe, the theory of relativity is always there, silently guiding our understanding of the world.